Hi everybody, hi, Mike here, and we're continuing our talk about electron configurations, and today we're going to change the subject a little bit and talk about atomic size and ionization energy and electronegativity. But first, where we left off last time, we were going to write the isoelectronic series, all those elements which have the same number of electrons and the same electron configuration. They all pile into the same orbitals, folks. 18 electrons, don't care where they're going to go except for in the same orbitals in the same fashion. So argon is the noble gas with 18 electrons. If we went over to the nonmetals, the halogens in the same family as fluorine, that'd be chloride ion is the stable form of chlorine, or one of the stable forms. Sulfur 2- or sulfide ion, all right, P3-, phosphide ion. I don't know why I put them in this order. I put the negatives over on the left last time. They all have the same number of electrons, doesn't matter. Potassium, 19 electrons unless you take off one, which is the stable form of potassium. That's 18 electrons. Calcium 2+, right? Let's even go a little further. Gallium 3+. Now think way back to when we first started. We just said, hey, here's the rules. Everything wants to have the same number of electrons as a noble gas atom. We never told you why. We didn't tell you about orbitals or quantum levels, and then we still can't tell you why this all happens. It just does. Let's even go further. 36 electrons. All right. Who's that noble gas? That is krypton. Well, that sounds like a Superman thing, but it's all right. Krypton. Huh? And so in the halogens, bromide ion. Selenium makes a -2. Now I'm gonna chicken out a little bit here and talk to you about what happens when you get low enough in the periodic table. Things get a little weird, and the octet rule doesn't quite get adhered to as closely. So I'm not gonna write down, go down below gallium and talk about indium. You know what happens over here, folks? What happens is, as you get further down the periodic table, the nonmetals run out and start to become metals. So there you go. That's going to put a nice tidy bow on electron configurations. Try some. Remember, you got the periodic table with every single one in the periodic table. See if you can throw darts at the periodic table and recreate the electron configurations. Now, let's talk about atomic size next. All right, folks, now we're going to talk about atomic radius, which is size. They're all spheres, right? So we like to keep track of how big they are with the radius, and that determines how they react. So atomic size increases as you go down in a family. So I can explain that. If you were to go in the periodic table, let's say the alkali metals, right? Each period you're adding a new n level. And so here is a diagram which I have stolen from either your book or the internet, showing the trend for atomic size. Okay, so you can see that as you go down in a family, the atomic size increases. We're adding shells, and it increases less and less and less because the shells become further, kind of closer together, I should say. What's weird is that, so let's summarize that. Down in a family, adding n levels. So what's up with this? As you go left to right, atoms get bigger. So if you go, I said that wrong. I'm going to edit that out. No, yeah. as you go right to left, atoms get bigger? That means as you go left to right, they get smaller? Don't they get heavier? Yeah, they do. They're adding neutrons and protons, so they get denser. Why is that? Well, the theory is that this is due to something called shielding. And what is theorized is that a filled shell of electrons sort of blocks an equivalent number of protons. So if you went over to, say, sodium, 10 of its 11 electrons are in filled shells. That leaves one of the protons unshielded, which means the 10 electrons shield 10 protons. So it's kind of like an effective charge of the nucleus of +1. Magnesium has 10 of its electrons in filled shells, and so 2 of the protons are unshielded, and so it's like the electrons are seeing a charge of +2, and so on. You go to aluminum, it's +3, and silicon +4, and so that's the theory as to why when you go across a period, atoms get smaller. Kind of weird, but okay. Anyhow, why do we care? We're going to introduce 2 terms, ionization energy and electron affinity, or ionization energy and electronegativity, which we will use to determine how things are apt to react. Okay, ionization energy is the energy required to remove an electron. So I made this atom, we called it M, because you know what, this is usually something we talk about with metals. And if you take an atom that is a metal, even if it's a very unstable atom by our considerations, in a vacuum with nothing around, it'll hold together because the nucleus is positive and the electrons are negative. So let's even take, like, say, something like a lithium ion. Or how about, remember when we threw potassium in water during class? That's, you'd say, hey, that's unstable, that doesn't hold together. Well, that's because there's a lot of energy available at room temperature in water or whatever, and that can supply the ionization energy, which will take a potassium and remove its electron to make it K+. But in a vacuum, it hold together, it required energy. It would require energy. So it turns out that I want you to think about this. If you were an atom and something was going to put energy into you to take it and kick its electron off of you, and make it go away and ionize, would it be easier if you were a bigger atom or a smaller atom? So let's think about that. Where's the positive charge in an atom? It's in the nucleus. So here we go. There's protons. Could be one or a bunch, but and then you got the radius. There's an electron. The bigger that distance is, the easier it is. Oh crap, I just totally... Hold on, I burped during that anyhow. Okay, so here's an atom. Where's the positive charge? It's in the nucleus. There's an N level, that highest out N level. We could call this a potassium or whatever. And if no competing energy is around, this holds together because positives attract negatives. Now, if you were a bigger atom, it would be easier to separate your electron from your proton, right? And if you're a smaller atom, it would be harder. So ionization energy increases as atoms are smaller. All right, so increases as atomic size decreases. So let's take this thought experiment. We're going to take one of the alkaline metals, we're going to put it into water, and we're going to watch it react. I'm going to put a lithium into water. I'm going to put a piece of lithium into water. I'm going to take a piece of sodium and put it into water. I'm going to take a piece of potassium potassium, I'm going to put it in water, and you're going to find that the potassium reacts way faster than the sodium does, and the sodium reacts way faster than the lithium does. And so this is an important thing with redox reactions. It's easier to take an electron off a potassium than it is a lithium. And so this determines how stable different metals are. All right, guess what, folks? We can now put metals to bed for the rest of the semester. Gen Chem 2, they'll come back. But that's it for discussing metals, because we're going into non-metal territory now. So we're going to talk about, and by the way, I don't know how much your homework goes into great detail. This is first ionization energy, and I'm just going to leave it there. We could talk about the energy to remove a second, third, fourth electron, but let's just talk about removing an electron and thinking about how would the alkali metals, who usually lose one electron, how would they stack up in terms of how high their ionization energy is. All right, next topic. You've been seeing it all semester on this periodic table, and this is why I chose this periodic table. And we've talked about this a little bit. Electronegativity. That is something that is a measure of an atom's tendency to hold on to its electrons. So let's focus in on the king of electronegativity, which is fluorine. Now, if you say that an atom is going to hold on to its electrons, right? Who's going to hold on to them tighter? The smaller electrons that can, the smaller atoms that can get those electrons closer to the nucleus. So fluorine, being at the sort of up and right of the periodic table, is one of the smallest atoms that participates in bonding. Hey, how come they don't do the noble gases? Well, they don't really bond until you get down to the weird part of the periodic table at the bottom. So fluorine has an electronegativity value of 4.0. So it's all relative. Electronegativity is a way to compare elements. And so you're going to go, let's go all the way to the bottom and left of the periodic table. Okay, I lied. I said we were done with metals, but this is just an example. Francium has a electronegativity of 0.7. Let's go further left and down than fluorine. All right, so the bigger things like silicon. Silicon is 1.8. All right, and so if you go right of silicon, chlorine is 3.0. So the further right and up in the periodic table you go, the higher the electronegativity. We're going to talk about that next time when we talk about how nonmetals bond with other nonmetals, and see you then. Ask questions if you got any. Take care of each other and yourselves. And scene. Oh no, let's go look at my asparagus. Hey, check it out, that's me. Bad photography. Don't show the shadows, Mike. Look at, I got numerous. Hey, welcome, little guy. I'll let you grow up. But you two, I will chop you off like a parasite. And, ooh, crooked. Okay, we'll let you straighten up. Then I'll chop you off like a parasite. Okay, thanks. See you guys later.